Uh, yeah, we'll get started on the topic today. So the topic for today was basically trying to find out like what does natural language generation means and how its applicability in terms of the conversational agents. And ma'am gave me a brief introduction about like who I am. So I just wanted to give a background. So I did my undergrad at MIT campus at an university almost a decade back. And then I went on to do my education, doing my master's in computing science at University of Alberta, where I did my thesis on machine learning. And then I'm also moved into industry where I work for the Verizon based in India and US. And then I also work for an electronic medical record company called Epic at US. And now I'm currently a machine learning scientist working with Alberta Machine Intelligence Institute in Canada. So it's one of the three pan-Canadian AI institutes. So Canada has an AI strategy. So one of the three institutes that is actually funded by the federal government, and it is associated with the University of Alberta, Simon Fraser University, and University of British Columbia. Yeah, and also regarding the talk, like, I mean, if you do have any questions, feel free to either put it in the chat window or feel free to ask me, stop me wherever it's possible. It might be difficult to actually keep a track of the chat window, but I'll try my best as much as possible to keep a track of it and answer your questions as quickly as possible. Or else, like, we also have some time at the end where we can actually try to, have that conversation, and I'll try to answer the questions there. Moving on to the outline of the talk today. So the plan is to actually divide them into like three high-level sections. The first section is just giving you a lay of the land about what does NLP means, and then we'll get into natural language generation, walk through one of the language models, and then we can talk about the conversational agents. So in terms of overview of the NLP, so natural language processing in general is more about like what can we do in order to process the data that is communicated by humans. So it could be in the form of text, it could be in the form of speech, like how does human understands it, and what does like human actually interpret and actually communicate to other humans. So we want the machines to actually learn how this human communication works in terms of text or speech, and try to make augment our intelligence with the machine intelligence. So one of the main questions is like when we talk about natural language, what actually makes it a natural language? Does it have some properties? So rather than properties, we can call them as like anti-properties, where like it doesn't follow certain things. So we'll go through one by one what those mean. So a natural language typically has like ambiguity associated to it. So the ambiguity could be associated with the subject or the topic. So one of the examples here is like Sarah got the bath ready for her daughter wearing a tutu. So the main question is like, who was wearing a tutu at that time? Like, is it the Sarah or it's her daughter? So there is an ambiguity in terms of the text that we provide. And one more example of ambiguity is around like the phonology or the sarcasm of it. So phonology in the sense, the tone really is important when you say it. So for example, I can say, I have never tasted a cake like this before, but does that mean that if the cake actually tastes good, or does it mean the cake tastes bad? So there is an ambiguity around it. And even sarcasm, like when you provide any kind of like sarcastic, especially during text, it's usually confusing. So that's still ambiguous. The second property which makes it a natural language is redundancy. So redundancy, like we try to use a lot of additional words in order to complete our sentences. So for example, it's deja vu all over again. We don't necessarily need to have that all over again. Deja vu literally means like it had happened before, or you actually have a feeling that it happened before, and now you are thinking that it happened again. And same way, I heard it with my own ears. So we don't necessarily need to say that we have our own, we heard it with our own ears, because it could just be said as like, I heard it. So that kind of redundancy adds to the complexity of actually processing this natural language. And then there is a literalness or non-literalness. For example, different statements can actually have the same meaning. So one example here is, I'm going to call it a day, or I'm going to stop working now. It literally means the same thing, but you could see the different set of words that are being used. So and the next is around the context part. So let the cat out of the bag. So it also means like you can really say, let the cat out of the bag, or you can also say like, okay, do you want to actually spill out the secrets? So it means the same thing, but based on like the context, it could mean different things. And in terms of poetry, So, like, I mean, we have poets who have written languages, but not necessarily in terms of like full phrased sentences. So one example is over here. So we can, as humans, can understand, but how can we actually make the machine understand? So these are like some of the properties which actually makes a language a natural language. And then we'll talk a little bit about what makes NLP difficult. Like, I mean, languages have been there forever. We have like now supercomputing powers where we could, I mean, a lot of understanding research has gone on under like from the linguists about the language. But why haven't we yet solved the problem of like NLP? And some of the reasons that we could think about is like the whole idea of natural language is not standard. So, like the language evolves a lot. And one example is like, especially if you take all the tweets, like you have something like, great job, I'm so proud of you. So for us, so with any number of O's means the same thing, whereas for a machine, it might mean different thing because your encoding would differ. And same way, the start of hashtags. So that becomes an issue. So having this non-standardness in terms of the natural language makes it a little difficult to process it. And in terms of segmentation issues, so we can have this idea of like New York is better than York. So New York and New York both are cities, but how do we let the system know that New and York are the same entities? So they are not two different words. And same if you take about the next sentence, the New York hyphen New Haven. So if you're not really processing the punctuations in the correct way, York and New becomes single word. And then there is a new, the predecessor new, and the post of Haven. They are just two different things. So having these kind of segmentation issues of how people write things. In terms of idioms, so he is a dark horse. So dark horse means something in terms of, in terms of idiomatic phrase, but you can also literally call having a dark horse over there. In the same way, I'm getting a cold feet, so it means different things. So having these kind of idioms makes it difficult. And the other thing is also in terms of neologism. So neologism having like the words that we kind of like invent, but it's still understood by humans. So one word that caught up was the retweet or tweet. So tweet literally is just the birds chirping sound. But we have started using tweet in the context of Twitter, and then there's a retweet associated with start creating new words, and even bromance. So it started from romance. Bromance is not really a word that was derived from English, but now it has been accepted in it. And then there is like the world knowledge. Like we take most of our decisions based on the knowledge that we already have within. So in terms of like Adam and Steve are brothers and Adam and Steve are fathers. So if we put in these two statements together, how do we know like Adam and Steve, they refer to the same thing? Or are they fathers, as in are they couples, or are they fathers of two different people, or are they fathers in joint custody? So there are a lot of things that happens. And even in terms of like tricky entity names. So one example is like which way for a bug's life. So A Bug's Life is like a really famous animated movie. So if you're asking for which way for Bug's Life, you can ask, an operator or a theater operator is asking them the way to the specific theater. But here, but if you think about literally, it also means like which way for a Bug's Life could mean completely different things. So having these kind of tricky entity names, bug versus A Bug's Life as a movie name, becomes difficult. In terms of concept drift, we also talked about like evolution of the thing. So when I say I want to buy a mobile, so in today's context, it means a different thing. Think about the context like 20, 30 years back. Mobile phone didn't exist at that time. So does it mean automobile, or does it mean like snowmobile? So there could be any type of mobile, or is it just a mobile telecom that you cannot really take and be mobile itself? So there's a concept drift. And even like if very recently, if you think about it, like just 20 years back, if you say, okay, Google is a new technology company to look out for. So if you try to process the text now, it really doesn't make sense because Google has already established itself as a well-known company. So these kind of concept drifts and all these different properties makes whole processing of NLP difficult. So, and that's one of the reasons that it hasn't been yet cracked to the level that we actually wanted to. But at least in the last few years, there has been like leaps and bounds of improvements in terms of NLP. So there are specific perspectives and paradigms associated with the NLP, because NLP is not necessarily a field which is only related to computer scientists, but a lot more people. So we'll talk about them. So computational linguists. So linguists are the people who take from the approach of a language, and how they can actually build computational models in order to use them. So, and then there is cognitive science too. So how actually we think, do we think in terms of a certain language? Do we do our math in terms of a certain language in our brains? Or do we even communicate with the brain? So are the brain waves associated with it? What is the perception of it? What is the cognition of the language? All those go into the cognitive science. And then we have computer science, where we actually lay down theoretical framework in terms of like how to build up certain models and build proofs towards it. And then there's information science, a group of people who would do analysis and the classification around the text that we retrieve itself. So these are some of the NLP perspectives, and it's coming from like various different fields and of arts and science. And then there are paradigms associated with NLP too. So when we talk about NLP, I mean, more recently, if someone is new to NLP, they think NLP is more like a machine learning approach. So machine learning is one of the tools to actually apply in order to solve some of the NLP problems. So, I mean, traditionally, it has been more in terms of symbolic approach. So when you think about it, like things like rules-based like expert systems, or even in terms of like the context-free grammar, the parsing tree that we all build, all those are symbolic approaches. And then there is statistical approaches, where we try to use like statistical modeling, and more recently in terms of neural networks, how do we actually do it, and how do we actually learn from the data? So some of the NLP paradigms lies around like very broadly in those two views. Yeah, so now we have seen a little bit in terms of what does NLP and why it is difficult. Let's get into what are some of the NLP tasks that are associated. I mean, there are tons of them. So I've done my best in terms of like trying to utilize one framework to see what are the different types of tasks that we can associate it with natural language processing. This is again adapted from one of the articles from KDD Nuggets, and you would find different way, and none of them is right or none of them is wrong. Try to use whichever is useful as the framework. So going forward with this KDD Nugget framework is that you could think of them as like at a very high level could be divided into 5 different tasks. The text classification. So we'll get into details of like how these tasks are associated. Then there is a word sequence task. Then there is the text meaning, regarding like the meaning of the text itself, and then how we can actually think about the sequence to sequence task, where your input is a sequence, output is a sequence, and then there is a dialogue-based systems associated with it. And when I talk about these like 5 different NLP tasks, what happens is they are not necessarily mutually exclusive. So what happens is these tasks usually in practice overlap a lot. That means you can have a word sequence task as well as a text classification task together. And as we go through the examples, you'll try to understand a little more in terms of how these are actually associated with each other. So whenever we think about this, these are not really mutually exclusive. And for any real world task, you would have to have a combination of one or more of these in order to arrive at results. So in terms of text classification, so text classification is pretty, putting it in a naive way, it is more like you're going to find out the results or do the classification based on the words that are available. So I'm not necessarily on the on the sequence or the order of the words that is available for you. So one example would be in terms of like determining how your emails is classified. So giving you an example of the emails, let me just jump onto the next slide. Yeah. So if you think about emails, you do have your primary email, but at the same time, like more if you're a Gmail user, you might have seen like you have social, you might have promotions, updates, all tagged automatically. So what it does is it tries to read through your content and tries to put them into one of those buckets. So having these kind of predetermined classes associated with and classify them into certain things is one of the text classification tasks. And again, like when you think about it, you don't necessarily, so if you're thinking about a spam email, you don't necessarily need to have a spam word coming after a nice word or wrong. So the systems itself are like really well established in terms of identifying irrespective of where those spam words or sentences are in your email, so that they could differentiate and put them into either spam or not. The other application, or one of the examples of doing text classification, is the document classification. And this has been like a really useful in terms of whenever you're trying to digitize your old content and trying to make it into something that is usable and searchable in terms of like either databases or file systems. So the kind of like some of the examples would be around the legal documents. What are the different case types? What could we extract from the different documents? Articles, especially when it comes to news. So the news agencies have started using machine learning to start dividing their articles into multiple different types and trying to personalize it to the user. And then again, like grouping of the documents itself. And then there is like other aspects to it in terms of text classification, which is like doing a sentiment classification. That is basically trying to identify the polarity of the text, whether it's a positive or a negative of a negative things in a text. And that could be identified using some of the keywords that could be formed in the text. But again, like, I mean, when I'm saying we could identify, it's probably more in terms of there are definitely outliers here. So one example would be, so if I ask you, you have done a good job, but I expected more from you. So what happens there? So it's either like a positive or a negative comment. So now, even for humans, it might be difficult to actually identify if it is a positive or a negative comment. So think about the system. So they go with the probabilities and trying to identify whether it's positive or negative. So, and again, like here, gives a simple example of positive negative, but people have gone beyond in terms of actually defining a spectrum, like between 0 and 10, where does this lie? What kind of positivity or negativity is there in a comment? And especially this has been more useful with the, with the advent of like Twitter, where a lot of people are actually explaining themselves on Twitter, their emotions on Twitter. And talking about emotions, one other classification task is around the emotion classification. It's kind of like a natural extension to what we do in terms of like sentiment, but instead of putting them into either positive, negative bucket, you can put them in terms of like multiple emotions. So the more recent research, and again coming out of university lab, is around like 27 emotions that could be identified from a text. And these emotions could again be in terms of like multiple emotions could be associated with each of the texts. So not necessarily only one emotion has to be for each sentence. So you can think them as like multi-class, multi-label classification problem. Yeah, moving ahead with the second type of like NLP task, or the second bucket of NLP task, which is going to be on the word sequence task. So the word sequence task is around the order of the sentence itself becomes a primary factor in order to arrive at certain results. So some of the examples would be terms of like identifying the missing words. So in order to know the missing words, you need to understand the syntactic and semantic relationship in the text. So the order, the sequence itself becomes a primary driving factor in order to extract those words. And the meaning of the words is also associated with the context itself. So some of the examples would be around like part of speech tagging. So when we think about like trying to identify what are the entities or the pronouns or the verbs of like different parts of speech in a sentence, the order of the words play an important role. And especially in terms of like parsing into compound sentence. If I have a sentence that is like says about 3 different things, how can we extract those 3 different things in the sentences? So building this kind of like parsing tree and extracting the specific part of speech has become, is primarily important. And then there is like the named entity recognition. So for example, if we have a text saying like back in 2000, People's Magazine. So does people mean like people as us, or does it mean a different entity? So trying to extract that entity from the text so that you could, there are like various further uses of using this entity, like, and we'll look at one thing called topic modeling too. So identifying that entity becomes a primary reason, and how we can actually extract that entity depends on like the text that is either predecessor or the successor of the text. So the order of the words becomes important here. And the next, there is like a co-reference resolution. So in terms of co-reference resolution, this is quite an interesting one too, because sometimes like humans are also not so good at it if you think about it. So one example here is like John went to the store, he bought a skateboard. So one of the pronouns here is actually he. Who does the word he refer to? So for us, it's pretty straightforward because we have identified an entity called John, and he would probably mean John. So on that, we can say that, okay, he actually refers to John. Now we talk about the second sentence. John drove the car into a tree and the vehicle was damaged. So now we want to identify what does this vehicle mean? So we already have a knowledge that the word vehicle is associated with the car. Think about someone who has never heard of either the vehicle or the car. For them, it gets difficult. So having that kind of knowledge really helps in terms of propelling it. And our systems are easy to identify, even though given the state of the art right now. So car and tree, so vehicle can be associated with a car. But the next example is pretty interesting too, because I've also seen some of the systems not really actually working well. So one is John drove the vehicle into a tree and it was damaged. So now the question would be around what does it mean? So it could mean vehicle or the tree. And it's a really tricky situation because now it would depend on a lot of other factors. Vehicle, are we talking about a truck hitting a small tree or a car hitting something like a banyan tree? So now the context is around like we need to have more information in order to arrive or resolve what this pronoun it means. So yeah, so and having this kind of like text around it helps in terms of word sequence. And then there is a speech act recognition task. So speech act in the sense that if I'm saying a sentence, so we can understand whether it is a question sentence or whether it's an order, whether it's just a statement. But for computers, it might be difficult. Is punctuation sometimes help? But sometimes, like when you talk about even exclamation, oh, what a way to go. When we start something with a sentence, generally it's a question, but it's exclamation and the tone, like phonology that I was talking about. So even in terms of like order, can you please do it versus New Delhi is the capital of India. So how do we actually try to differentiate one is an order and one is a statement? So those things are also part of the text. Sorry, in terms of the classification task. So next is the text meaning task. So text meaning task is really trying to identify, trying to identify what that exact meaning is and trying to extract the meaning of it. And it could be done based on just the sequence of words or giving more context around it. So, and it goes beyond in terms of like just words or the group of words that are associated with it. And then we, at a very high level, we also have the topic extraction task, which is going to be around topic modeling. Like give it a bunch of text, like say a document. You want to identify the main themes of it. So doing this kind of topic modeling, like using both supervised as well as unsupervised learning usually helps in terms of extracting the theme, and then probably take it and say, okay, we are going to put them into like multiple buckets, or we want to actually extract or automate some of the tasks in here. So there are various applications in terms of extracting the topic itself. And yeah, and our approaches are like topic modeling, which is usually an unsupervised way, or the topic classification, which is a supervised way of doing topic extraction. And then there's the idea of like text summarization. Given a text, a long text, we want to actually concisely put them into smaller one. And this, this idea of text summarization has become more popular more recently. And you would see a lot of apps that are coming out there that actually tries to do this so that people don't have to, for example, don't have to read a whole book. They can read a book in like X minutes. And there are like a lot of companies out there which are trying to take advantage of the novelty in text summarization to help to deal with books. So, and the other one is like identifying the supporting text or evidence. And this is an application which is more in terms of like, for example, the fake news identification or the misinformation identification. So you have a supporting text, all the knowledge that you can get. And then there is a statement which says, okay, for example, my example here is like, given this text of around John is a great person, he's a well-established person, and then giving more context about the thing. And then there is a statement that says John has never had any cases against him. So first thing is this claim even true or false? Would we be able to find it? If it is true, what is the evidence that is supporting it? And in some cases, if it is false, what is the evidence that is supporting that that person is not doing, that the statement doesn't hold good true anymore. So how do we try to extract this supporting text or the evidence? And the next kind of system is actually the question answering system. So that means given a question, you provide an answer. But in order to provide an answer, can you extract information from the question, or then there is a separate knowledge base that you need to actually go and extract the information? And is the answer even coherent? what are the supporting documents, and does the answer need to contain supporting document, or do they need to just given them as facts? And how is the knowledge even represented in terms of the supporting answer? One example is, and yeah, this is an experiment that we tried out, like asking an automated system to say that the sky is green. So uh, sky, cannot be green, at least in, in majority of the cases, unless there isn't a, like aurora going on there. But if the sky is not green, the system has to understand that it's not just a color that the sky can be, but it has to be specifically either in terms of like shades between blue, oranges during sunrise, sunset, or very dark, close to black during the nighttime. So it has to have that kind of knowledge, and represented and understood by it, and it cannot randomly just generate in terms of saying that the sky is a color and replace any color with any other color. And in terms of the applications, like identifying even like what are the options that are available from a given list of options, and that options are actually sent as answers. And then there's other task of like the sequence to sequence task. Now we can start seeing like how multiple of these things are actually overlapping. So when I talked about text summarization, I told you that we have a list of, a long text given, and then the extracted, there is a summary of it. So when we talk about sequence to sequences, what it says is you give a sequence of words to the system, and you expect sequence of words as an output from the system. So this is also an example of what we do with text summarization, which is again like the text meaning task. So now we start seeing overlapping. Even in terms of question answers, we provide a question, which is again a sequence of text, and we expect an answer, which is again a sequence of text. So some of the examples, and we are starting to see some repetition here, is like rewriting or doing sentence completion, or doing the text summarization, question answering, language translation. So language translation has been more recently a really uh, like an application that has been very pervasive. And for example, this is here in Espanol and English, where they say, okay, whatever that has been there in terms of a different language can be translated to English, or vice versa, or any two languages for that sake. For that, we need to have understanding of what those language means and what the grammatical rule means. Um, One way of doing that would be actually understanding the grammar itself, but more recently, deep learning techniques try to learn and understand them by selves. So we don't have to explicitly give out those kind of like grammar for them to work well. And the fifth type is around the dialogue-based task. So where, again, like we give an input as sequence of words and we get the output, but now it is around like what exactly do we need to want to have from the system. So are we asking question and answer, or are we asking it to take some action? So especially if you think about more recently Google, Alexa, or Cortana. So what they try to do is they can like switch off your lights. They can start playing something on YouTube for you on your TV. So you want them to take an action, or do you want them to just respond, like asking questions about what is the weather like today, or you would just want to actually have a conversation with them randomly. So it doesn't have to be really a meaningful conversation. So there could be multiple things that you can do. And now if you see the speech act recognition, identifying between a question versus an order is a part of it. And then there is a sequence to sequence task, a part of it in terms of dialogue-based system. So now you could see that there is an overlap between these different five NLP tasks that we were talking about at a high level. So, and then there is a co-reference resolution, also part of the dialogue-based system now. So even the dialogues need to actually resolve the pronouns in order to rightly answer or query or respond or take an action to whatever is being actually asked to the chatbot system. Yeah, and generally, if you think about like the research that has been done in more, so in terms of like academia, it has been more towards like there is a lot of NLP papers are coming out, and so this is a pretty old one, as in like I think it was like July or August 2020 where ACL was conducted. ACL is one of like the big conferences that in terms of like computational linguistics. So some of the high-level topics that were there are actually represented here. So mainly they include the machine translation, the question answering system, sentiment analysis, summarization. So these are some of like the hot topics that are right now actually being researched upon by academia. Sorry. Yeah, so that gives an overview about NLP, kind of like gives an idea about NLP task and other things around it. So maybe we can take some quick time to see if you have any questions so we can answer it before moving on to the next section. Okay, yeah. So we got a question here. So can we prefer pre-trained models to do these tasks? If you can use, yeah, if you can use some pre-trained models other than blood. Yes, I'll answer this question. That's going to be a part of this the next session that is coming up too. So in terms of like what does pre-trained model mean, and I'll answer you. And if I'm missing out on answer, like I'll definitely answer you at the end of the talk. Thanks for your question. Okay, so what I'll do is I'll quickly move into the next section in the interest of time. And if you do have any questions, please put them on the chat, and then we'll go through one by one if we have time. So in terms of natural language generation, so now all the while we were talking about like what does NLP means, the processing of natural language means. Generation is like kind of like a subsection inside NLP, which deals completely only with the generation of data. So you have an idea of like, okay, you can do analysis on the data, you can try to understand the data, but you also, in order to communicate, you also need to generate the data and let it go to, let it go towards either another agent or to humans. So the idea of like the process of producing meaningful words, phrases, or sentences from structured data. So although the word structured data has been like, it's the kind of like a gold standard definition, but what is the definition of structured data itself has been evolving. So previously structured data means like you can actually try to query and extract like information from it. But nowadays with deep learning models coming up, all these things have like started being a little bit loosey-goosey. So the definition of structured data itself is not something which could be comprehended by humans at the moment. So, and one of the answers is also around the pre-trained network, like how it could not necessarily be a structured for humans, but be a structured for the system itself. And the main idea of like natural language generation is around what machine learning produce, so that it could communicate either with the humans, or humans can communicate with the system, and sometimes like one agent communicating with the other agent. You might have seen certain examples where people have started putting like an Alexa and a Google Assistant together and ask them to have the conversation. Other things are Twitter bots, where Twitter bots try to interact with them. And you might have also seen an example that was done by Facebook where there were two agents that apparently started building up their own language and started communicating with each other. Two agents as in like the two bots. So yeah, so that's what the natural language generation means. And very specific to natural language generation, again, like there might be some repetition in terms of the task that we have already seen, but we can now focus on specifically on the natural language generation. So one is the first task will be around like creative writing. Can you train on a specific set of text? So one example is like Shakespeare writing. So people have trained on all the Shakespeare books and asked the system to write novels in the Shakespearean English language, or even in terms of poetry, people have given a set of like poems and asked them to write poems too. So creative writing, image captioning. So given an image, what is the story that you can actually tell about an image? And here, if you see, for example, there's like mountains. So if you think just in terms of object detection, you can bring out some keywords like mountains, clouds, trees, lakes. But how do you build a story around it? So for example, here you could say 2 logs of wood are floating on a lake in front of the mountains on a cloudy, rainy day. So that's where the whole idea of natural language generation comes into picture. and then writing a really coherent story on that. And the next is also on the summarization part. We did see in terms of giving a long text and getting a very concise or the gist of the story. But if you think about it, there are like two ways to actually do it. First is the extractive summarization. For example, if you have a paragraph with 10 sentences, extractive summarization tries to identify which are the most important sentences and then just frames it. Whereas abstractive reads all the 10 sentences and then rephrases it everything so that you still get the gist, but not necessarily having exactly the same words or the same sentences that were there in the original paragraph. So here is an example of what happened here. So this is using like one of the models called T5 models from Google, and this is a real example where it was given a set of text and asked to summarize. In some cases, it did summarize based on the sentences that were also there. So sometimes abstractive can become an extractive. But if you see, like, the word April doesn't really appear on the original text. So it says May 1st. And probably because there was also a word called previous. So it, for some reason, it tried to assume it to be April. So again, like, there's a shortcoming in there. But again, if you see, it knows about the knowledge that April comes before May and tries to utilize them. And also, if you think about it here, if the second sentence right in the middle where I'm highlighting, it says he said, but doing the co-reference resolution for this he to the president because the topic is around the president and replacing it with the president here, the president says. So that's something, again, like, the system has tried to do it on its own without any human input there. So, I mean, that's the kind of like the state that we are in where models are getting really good in terms of summarization. Yeah, and in terms of question answering system too, again, like at a high level, you can think them as the same logic. Like, can it be an extractive question answer? So what Google does currently is more on the extractive side. Like, for example, if you give an example, like, what are the best language models? So what it does is it provides you a statement inside one of the web links and tries to give you that as an answer. You can try that out. Or you can ask any question which needs to have a long answer, like how to do something, and it'll give you a specific paragraph inside a web page saying that this is the answer and put it in with the results itself. So that's the extractive summarization that Google does, where you process the question, retrieves the document, extracts the specific content, and just frames the answer for you. Whereas the abstractive question answering system is like, it does everything the same, but it goes through the whole content and then rephrases everything for you to give it in a short, concise gist. So you can think about a web page having an answer in the first paragraph and, let's say, the fourth paragraph. So a good abstractive summarization system could, a Q&A system could try to read through it, combine these two together, and make it into a single statement and rephrase it and give you as an answer. So that's in terms of the question answering system. And then there is a dialogue-based system. And again, there are two different perspectives, not necessarily orthogonal, but two different perspectives of a dialogue-based system. One is the purpose of it. What is the purpose of the system itself? So purpose could be really generic, like that's like an open-ended system, or it could be specifically goal-oriented, especially when you talk to chatbots and let's say the customer care of a banking system. It will try to actually be having a goal of like giving you more information specific for that bank. And then there are generic systems that are out there, which is like open-ended. And in terms of the information too, it could be open domain that it could talk about anything, or it could be, again, like same example of banking system. If you take, it's going to be closed domain that it can only understand banking. Or if there is a customer service that can only understand about that specific service that the customer service is providing. So dialogue-based information system. And like one of the more recent ones is the machine translation. So when I say recent one, in terms of not necessarily a new one, because machine translation has been happening for decades. The machine translation over here is more like how well they have actually adapted in terms of translating from one language to another. So language one. So if you have an input as a language one, what it does is it encodes it, then creates a representation out of it, and using that representation decodes into the second language. That's like a broad thing about what does machine translation means. And again, machine translations have been having for decades. So initially they were all based on rule-based systems. So like creating that kind of grammar, identifying those rules using expert systems, and then trying to do the translation between one language to other. And then there is a statistical method. Uh, and then there is also neural machine translation, which is more of state of the art. So in rule-based system, what it does is it creates those kind of like dictionary around it, creates those grammar rules. But creating these kind of n number of rules becomes, it's not one of the best ways to arrive at in terms of scalability of the results. But the huge advantage that it has is that it could be explaining the translation of what are the aspects that it took from language one and translated into language two. And in terms of statistical machine translation, it's like using statistical models to actually build and learning from the parameters of the data itself. And one of the examples is using term frequencies. We'll see an example about the term frequency. And then it can be phrased or word-based, or even at a very hierarchical level where you go at a high level at the document level, then go at a paragraph level, then go at a sentence, and then the word level. And neural machine learning is like still based on like what statistical machine translation does, but making more leveraging the advantage that we have in terms of like the deep learning and the neural networks. That's why the neural machine translation. So in order to do these kind of like translations or even arrive at generating a language, like saying a statement, can I go there, or I'm a good boy. So trying to generate that, the process of doing that is called language modeling. And in order to do language modeling, what helps in terms of a model itself is a language model. So very, again, naively put, a language model is just going to be a probability distribution of a sequence of words. Mathematically, that's how it works out in terms of like, given the sequence of like word of like, let's say, I'm just going to say, I'm a good boy. So I am a good boy. So all these 5 words together are just going to put in terms of what is the probability distribution of having these words in that specific order or sequence. So, and what does it do? It tries to predict words. So if you give an example of I, it tries to predict what would be the next word. And especially you might have seen in terms of writing emails or even working with Google Docs, it tries to predict what the next word is so that it helps you in terms of completing your statements easily. So for example, I found a cat under the, so what would be the next best word? So that's what it tries to predict using the whole language model. So it could be a chair, it could be a table, it could be a deck, it could be a tree or a bed. So which has the most probability of, being in that specific, filling up that specific blank in this specific context? And how can it be formally defined? So in terms of probability, it could be defined in terms of the conditional probability. So probability of having a chair, which is going to be my xt over here, given all the previous words that it has seen. So that means probability of chair given probability of finding my cat under the probability of table given I found the cat. So what is the probability of it and how do we do it? So this is a very simple way of putting how do we arrive at predicting the next word. So, I've just expanded this mathematical thing in terms of what is the probability of getting that text. So given the whole sentence, that is x1 until xt, that means finding the probability of the last word given all the previous word, and then multiplied by probability of the last but one word given all the other words prior to that, and so on until you have the first word to it. So that's what language model does. And like every day we see this is how the language model helps us in everyday life. So Google search, it tries to give you a list of options by predicting. Again, a lot of factors go into it, but again, very at a simplistic way, we could say that it, yes, uses the language models specific to the probability of the input that you're trying to give. And then even in terms of the emails that you have, like for example, feel free to reach out to me. But if you see that the rest has already been filled up by the system, and it allows you to say if it is correct or not. And if you think about it, that's also a feedback for the system to actually train it better. So if you actually press the tab and say that, yes, it is correct, it automatically kind of sends a feedback to the system saying, okay, this person has this way or this style of writing. And same way, even if, this is a screenshot from like the WhatsApp app. So it gives you, can you please pick up the So sometimes it can go wrong, as you can see. Can you please pick up the good? It doesn't really mean anything, but it has found some kind of probability. And same way for roll or phone. Can you pick up the roll, pick up the phone? Most probably phone seems to be the right answer, but again, based on the context, it could mean different things. So how do we actually learn a language model in here? So learning a language model, again, like very vaguely put, it's not really uh, the only thing we can differentiate into, but we can put them, or the most accepted way is we can try to think them as like the pre-deep learning era or the deep learning era. So in terms of the, I mean, we'll go through an example, one example from each of these and see how they are actually different or how similar they are. So we can take an example of n-gram language model. So what does n-gram means? N-gram means, so each of the word, you could consider them to be a gram. So the collection of n words, you can call them as n-gram. So it's just a sequence or ordered set of n consecutive words. So one example is here, the teacher asked everyone to open their books. Unigram means just taking words individually. If you think about bigram, that's like taking sets of two words continuously, like teacher asked everyone to, and same way trigram and fourgram. So using this n-gram language model, we are going to see how we can actually build a language model from using just statistical models and not necessarily the neural or the deep learning models. So n-gram language models, so what it needs to do is, based on the probability that we were talking about, so probability of finding the next word given all the previous words. So, but specifically, I mean, I have just expanded this to show how we can use n-gram. So it's exactly the same thing. I've introduced the concept of like this t minus n here to reflect the fact of that word n. So what happens is, instead of conditioning my probability on all the words that I've seen before, we would be just conditioning based on the probability only for the last 3 words or last n words that I've seen. So in terms of example, if I give, so what is the prediction of the next word is probability of my current word. So if I take the example of 4, probability of my current word given the probability of my last 3 words. And in conditional probability, you know, like it's very, I mean, you can translate them into like P of A given B is P of A and B by P of B, sorry, yeah. So what happens is, so the probability of me finding out the whole n grams divided by my probability of finding n minus 1 grams. So that's the probability, and it'll be a little more clear once we get into the example. So I'm taking the same example that we had before. A teacher asked everyone to open their books. So if we talk about this 4-gram model, what we have to consider is the last 3 words only in order to do that. So if I'm taking this example of it, so what's the probability of me finding out to open there? That's going to be my denominator. And what is the missing word? So the missing word could be any word from the vocabulary. So for each of the word in the vocabulary, we have to identify which gives us the highest probability. And now again, having this probability, what we can do is we can actually try to approximate using some frequent statistics, which is like using the count method. So what is the count of that we found to open there with a specific word divided by the count to open there? So in a given corpus, let's assume that you have like to open there occurs 1,000 times. And now you want to identify which is the next best word. So what you have to find is for this corpus, how many number of times you have like to open the doors or to open the books. So you can list down like n number of possibilities in there and try to predict the word which gives the maximum probability to it. So here for us, just as a dummy example, in our dummy corpus, we use like probability of books given to open there has the highest. So we are saying, okay, the teacher asked everyone to open their books. So that now becomes, I mean, the next predicted word for us. If there was like some other word which actually had a higher probability, that would have become the best. I mean, the better word to be filling up that specific blank. And this is a very simplistic model in terms of how do we arrive at the next predicted word. So what are the shortcomings of this n-gram model that we have? First is losing out on the context. So we know we have seen the word like the teacher, and that's why we can say it's for the books. But think about if we replace with the teacher with the carpenter, and yet just go in the last 3 words, which means I'm just going to consider to open there. It might still predict books. So context-wise, it might not make sense. So we are actually losing out on some of the context, but at the same time, we cannot make the n so large because then it will be difficult having tracking and keeping everything, and the system just becomes first so slow and it becomes too sparse. And one of the examples of sparsity is like in the training, if they haven't even found a word that existed. So if you think about mathematically, the numerator becomes 0 now, and like even the denominator becomes 0. So there are ways to avoid those things, but sparsity is one of the issues when you think about just n-gram language model. So if I talk about it was gobbledygook, it doesn't necessarily have been part of the training, but it's still is part of here. So how do we generate the sentence? So in real, what we do is we provide them with the first 3 words and ask it to ask the system to predict the 4th word. And then we give the last 3 words and ask the system to predict the 5th word, and so on. So until we actually find some kind of delimiter at the end, you continuously keep on predicting the next words. So that's an example of like the n-gram model that we have in NLP. But let's talk about the neural language models. With the advent of like the deep networks, the neural network models have been really established. So first we'll go with, I mean, one of like the simple models of using neural network, and then we'll go into the advanced ones. So again, just as a refresher, I mean, you might have already seen this thing, so I'm going to just like cruise through all these quick details about neural networks. So typically what happens in neural networks is you have these inputs x1, x2, x3, x4, which are going to be like the features of an input. And you have these weights. So weights are the ones that actually a neural network learns on its own. So what it does is first there is a function of linearity. So it's very similar to an equation of a straight line, y is equal to mx plus c. So you add a bias, which is your c factor, how you want to actually move your straight line, and then multiply with the inputs and the weights that you have and sum them up. So now you got an equation of a straight line, but not always you can model everything using a straight line. Sometimes you have to use the curves. So in order to do that, there is an activation function which brings the concept of nonlinearity into it. So now we have like f, which could be anything. I mean, in some cases, it could be just adding a tan curve to it, or some cases it's more like adding a ReLU to it. So you might have heard about these terms over there. So adding that kind of nonlinearity to it. And this is a very simple model of like giving the input, it goes through a certain transformation and gives you the output. So this combination of linearity and the activation function is what we call them as neurons. And this could be combined into just one single thing and represented in this way. And I have 2 outputs here. This is an example of a classification problem. But if you want to regression, so instead of like a specific classified output, it might just give you a continuous number. So one neuron. So if we can have n number of such neurons in there in order to actually do this neural network. And the number of neurons that you have in the middle is actually a hyperparameter. So in the machine learning world, there are 2 types of parameters. One that is actually learned by the system. So those are the model parameters. And then there is one set of parameters that you would have to actually tune in order to arrive at some arrive at the best results that you have. So those are the hyperparameters. So the number of neurons that you have in this is a hyperparameter, and this layer is called as the hidden layer. So you have an input layer, hidden layer, and the output layer. So if you really have just one layer or a couple of layers, we call them as a shallow neural network. But if you have like n such of these networks, so everything is combined with each other at every single level, then these are called as a hidden layer. And if you think about it, the number of times that these arrow marks that you're seeing are actually the number of parameters it's learning. So that's why you might be, especially in the natural language processing, you might hear people saying models with millions of parameters. So these are all the parameters that the system tries to learn. So yeah, so this is all the deep neural network. And again, like there are so many variants of this, but it's like a whole course on its own. So in terms of language models, how we can try to do this. So we'll take a simple example of fixed window model. So what happens is, instead of taking this whole context, we again try to take only those 3 words to start off with. So what happens here is we give them as inputs to our neural network. So 2 open there. But these inputs really don't mean anything because these are words, and computer system understands everything in terms of numbers. So we have to translate these words into numbers. So there are various methods that could do it. One simple way that you might hear is one-hot encoding. It's literally translating each of the word into a combination of binary, a binary sequence, and that is your one-hot encoded vector. And then from this encoded vector, so now this is a one input with three words in it. So you would just concatenate. Again, there are various methods to concatenate it. I'm just using just simple concatenation in order to create the embedding layer. So this is going to be my input layer in terms of neural network. Now we go through either in terms of deep or shallow or any number of layers, hidden layers. You go through that processing, and then there's a whole idea of back propagation that comes into picture in order to fine tune it again and again. So once we have this hidden layers, the output that we get is actually a probability distribution of all the words that we could have, of which you can actually take the one which gets the highest probability and replace it with the blank over there. So this is how it tries to predict the next word in terms of neural language models. Inputs, translates them into numbers, then concatenate them to form the embedding layer, then go through the processing through the hidden layers, irrespective of number of hidden layers, and then finally arrives at a probability distribution. But again, like when we think about the fixed window, it still suffers from some of the shortcomings, but there are like two primary advantages compared to the n-gram model that we saw before. So n-gram model, when you think about it, you need to maintain the statistics for all different combinations of 4 words that are there and 3 words like n and n minus 1 in order to get that kind of like the frequency measures. So, but here we don't necessarily need to have all the parameters that we have learned are good enough to actually reflect the fact of that probability distribution. And then there is a sparsity problem doesn't really occur because now we won't be having a denominator of 0. Rather, it will try to find out the closest word. And that's where the whole idea of like embeddings all come into picture. In terms of shortcomings, what are the shortcomings that you can see? It still suffers from the same idea of just using the last 3 words. And then if you go into the mathematics behind it, the matrix multiplication that comes with it. So what happens is each of the words is actually done independently. So that means there is no representation of that sequence as part of this. So in order to address that, the RNNs were born, the recurrent neural networks. And it were also pretty straightforward in terms of like how we can do it. So let's assume we have a set of words x1 until xt minus 1. So the first thing is usual. We try to translate them into numbers. Now, these numbers, instead of concatenating them into one single embedding layer, you try to give them one by one. So what happens is you initiate a hidden state. So the hidden state is what we call them as the representation state. And after running through all these processes, that's what we call as a pre-trained network. So this is what people have been using in terms of either BERT or whether it's GPT models or the GLOV models, word2vec. All these are pre-trained networks based on some task. These hidden states have been fine-tuned. So you give an input, it runs on the hidden state. Now the same hidden, and you get an output, but the output is optional here. And then you run the same hidden state through the second. Now what happens is it tunes it specifically for the second word again, and then it keeps on doing it again for all the words until the sequence is over. So this avoids the problem of independently doing all those words together, but at the same time, the sequence order is actually maintained. How it is maintained? It's maintained internally in terms of how the hidden layers, the hidden states are actually tuned. So if you think about the example that we show here, when we provide the most probable next word that comes is teacher. And now what it does is it uses the and the word teacher and sends it to the same hidden state. Now a hidden state is framed and it's done for us, everyone, and so on until it finds a delimiter. So it avoids the whole idea of like this specifically just using those 3 words. And so that's why RNN models are pretty popular. This is a real world example of like things that were trained on RNN. But if you think about it, in terms of like creating a recipe, it created a chocolate ranch barbecue recipe. So chocolate and ranch usually don't go well with each other. And even if you think about the recipe, it never says anything about like adding chocolate anywhere. So it's just more like a random thing that it created. For someone who doesn't know about recipes, it might be possible that they might be looking at it, oh, this created a really well-written language. But when it comes to common sense about what the system could understand, it really doesn't reflect that fact. So what are the advantages of it? So now, if you think about it, like we are not really restricted by the number of words that can be in a sentence. Previously, we were restricted using just last three words that were there. So we don't have to restrict ourselves. And then we don't have to really maintain all those different combinations. And also, when you think about it, it doesn't matter whether you give this RNN network um, one document or thousands of documents, the size of the RNN network doesn't change. The reason, the hidden state size is always going to be the same. And again, like this hidden state is the end after training on a task is what we call them as pre-trained networks that like companies like Google's and Microsoft's and OpenAI have done. And that's what we try to use them to start a new process rather than trying to train everything from the scratch. And BERT is one of the examples of that too. The question that was asked around BERT. So there are other embedding pre-trained networks, and more recently GPT-3 has been doing really great. And then the other thing is around like using of the information from the past. So it does kind of like get the information from the past, but again, we'll see in the shortcoming why that doesn't help. And in terms of like the output, those are actually shared between the whole network, not necessarily per individual input. So that gives an advantage of like trying to understand the sequence of words as a whole. So some of the disadvantage, the computation is still sequential. People have still tried to take advantage of matrix multiplications and all, but the computation is still sequential, so the rendering might be slowly. And then there are long-term dependencies. So we have this issue of vanishing gradient problem in neural networks. So the more far away it is, the less it can be actually captured, and then there are issues associated with it. And in reality, that kind of like, although theoretically it still tries to take all the words that it has seen into account, but in practice, if you see, it really doesn't happen that way again due to the problems such as vanishing gradient. So some of the things that, I mean, advantages over RNNs have been in terms of like, yes, RNN-based models could be RNNs, or it has like the bidirectional RNNs, so rather than just going through a sequence from one way to other, also add one more layer where you could have the reverse. And then there are LSTMs. So when we talked about RNN, there are only like two neurons. One is like the linearity, and then there is like the tanh function or the activation function. But if you introduce a lot of complexity in terms of gates, so long short-term memory is LSTM. So what it tries to do is it tries to find out any dependency which might have happened in the past and tries to address it. So LSTMs or bidirectional LSTMs have improved RNN-based models. And then there are like LSTMs became more complex because they had a lot of units around it. So there was like gated recurrent units that, I mean, in most of the tasks have been performing well in terms of this thing. But the most important or like a mind-boggling leap that has happened is in terms of using transformers-based architecture. So all the well-performing, including BERT or GPT, so all the T in that, all those models actually stand for transformers. So these are, so this gives you an example or difference between what an RNN and what a transformer is. So transformer really uses an idea of like having multi-head attention network. So instead of thinking them as sequential tasks, you can think them as like parallel tasks, and all these words are sent in parallel from layer to layer. And also at the end, what you can get is also specific words that are more important than the other in this whole sentence. So what happens is it allows you to interpret what has actually happened. And also in terms of all the tasks, whether those are blue scores or rouge scores, all those scores, it has been breaking all the records that have been established previously by RNN-based models. So transformers have been like a huge leap in terms of NLP processing, and it has been used for almost all the tasks that are around there. So the 5 different types of tasks, whether it's natural language generation or whether it's even classification tasks, they have been performing really well. So this is the kind of like, I mean, we won't get into details of it, but this is what is actually happening inside the transformer-based architecture, where you have these kind of like multi-head attention, where you give more weightage to a specific head than to actually giving it to the whole sentence, and thinking about like making the RNN itself learn, but rather than that, you're trying to specifically focus on certain specific attentions. So, and then there was like the transformer-based models. So some of the examples are Transformer XO, which was one of the initial ones, but Google uses in almost all of its services. GPT by OpenAI. So this has been breaking all the records more recently. And GPT-3 could kind of like create text where it is even difficult to find out whether it was created by a human versus a machine. So uh, the reason being it is so contextually aware, and it could put the facts all that it has been trained. Just that the access to GPT-3 is restricted currently. It is open for some researchers, and it is also a paid model at the moment. So not a lot of experiments. I personally couldn't do a lot of experiments. So most of my experiments are around BERT and GPT-2. Uh, that GPT-3 has been performing really well. But again, like you need to have a GPU even to infer using GPT-3 models. For the matter of fact, even for GPT-2, you need to have some kind of GPU just for inference. I'm not even talking about training. That means you give an input and you get the output. You need to have uh, some form of like graphical units there. So transformer-based models, the main advantages are that they are not sequential, so it can greatly take advantage of all the GPU and the matrix neural engines that are there inside the GPUs. And they also put attention on like certain words that are most important. So to an extent, they could be interpretable, but again, in practice, they are not real. I mean, it's they are and they are not. So yeah, I mean, before going into the last section of conversational agents, I was just wondering if there are any questions around language models or natural language generation. We'll take around like 10-15 seconds. Yeah, we do have a question here. Great. So can we use data generation to create a data set or corpus? Yes, you can actually do that in order to create a corpus. So one of my current research is actually trying to find out the data augmentation techniques for like low resource data. So many of the tasks, especially in the medical industry, you get really less number of data in terms of text. So how can you actually try to generate it? Generate more data related to your original data so that you can actually train or use that as a corpus. It could be done. There is a caveat associated with it that, I mean, the kind of, whenever you're generating something, you have to validate if they are actually accurate or not, so that you don't have that compounding error effect. If there are compounding error effect, then there is no use of actually you generating the data. So it's currently still in a researchy phase. So I mean, there have been some successes, some failures, but it cannot be said that it is there across the whole domain of NLP. Again, it would depend on what kind of data there is, but it could be done. So will the data sampling, sorry, I would have to scroll up or down. Okay, so will the data sampling, downsampling decrease the performance of the model? It again depends on like how much data do you actually have. If you're thinking about like sampling down from 1 billion sentences to like 500 million or like a few million, maybe not. But if you're thinking about like from you only have 1,000 sentences, and if you want to downsample it to like 100 or 50 sentences, then there might be. And again, like how separable they are. So that's also a question around like in terms of like the linearity or the plane that could be then how differentiable they are. Okay, the next question is, how are we putting a nonlinearity through an activation function? Okay, so the activation function itself is the nonlinearity, because for example, if you take a tan hitch, if you draw a tan hitch curves, it looks something, okay, I might be doing it weirdly, but yeah, it looks something like this. So so that brings in the concept of nonlinearity. Or even if you think about like, let's say, I want to create a parabolic nonlinearity to it. So what I can do is just the function could be whatever I have summarized in terms of the sigma x, and run a 4x square on top of it. So that means even if I just write an x square on top of it, So it becomes a nonlinear function. That's how we try to actually make the whole idea of an activation function to be nonlinear. Next question, how abbreviations are handled in NLP? Yes, there is no straightforward way. There are libraries that are out there that tries to actually find out what is going to be for, even for the example of NLP. So natural language processing stands for NLP. There are like some libraries out there that are done. But if you have large enough corpus, and if you know about like something like word to vec, so it tries to take two different words and sees how close they are to each other. So in that way, both NLP and natural language processing, the word, could, if you actually have enough corpus, then you can see that they are very pretty close to each other in terms of the corpus. So you can do explicitly, or you have your models like huge enough training corpus so that you can actually do so that you can actually reflect on that fact that one abbreviation stands for some kind of like a full form. Okay, I'm just going to take this as a last question. So, I mean, here. So, do generative adversarial networks help in NLP? Yes, they do help in terms of trying to create trying to make the system better in terms of how well the input output are matching. But the thing that you should be aware is that what is going to be a function that you're going to give them for adversarial network. So generally GANs are used like where you want to actually provide them with an input and try to see if the discriminator is able to detect whether the input was actually generated by the system or it was already given as part of the system. So trying to discriminate between these two. So it tries to help good in terms of building the system itself. But again, it would be really dependent on the specific task that you want to associate or what you want to do with GANs. So one of my techniques that I'm using for data augmentation is also use GANs for it in terms of like, can I augment more data by trying to fool my discriminator and generating a lot of sentences. The moment I get successful, that could be used as my training corpus. Okay, so we just have 15 minutes left, so I'm just going to rush into like the conversational agents. So this is going to be a little less technical in terms of like what is done. So we'll go at a very high level. So conversational agents are really going to be a dialogue-based system where either you can have conversation with or something that helps you make decision. Like you can ask questions to it and it'll help you navigate the conversation in a way so that you can come to a decision. So those are like very specific chatbots that are out there. Or if you want to take specific actions on behalf of it. So one was like switching on the lights or switching off the lights. So common names for these kind of conversational agents are around like chatbots, dialogue systems, text-based assistants, or personal assistants, depending on the utility and also in terms of the marketability of the system itself. So we talked about like these chatbots could be divided into two types. One is on the purpose, one is on the information. Based on the purpose, it could be generic versus goal-oriented, or it could be open domain versus closed domain. So at a very high level, this is the architecture that we have in terms of the conversational agents. So you have a text input, you send it to a system, you form something, and then you try to create more text and you give them as text output. So the first component that is there is actually trying to understand what is actually being sent as a text input. After understanding it, it does some processing, creates a representation. So this is again like the pre-trained network you can think of, or any kind of like representation. And then it tries to generate an output. So in the NLP world, this is what we, and specifically in the conversational agent world, this is what we call them as like the natural language, or NLU, natural language understanding, as the first unit. And then there is a unit of natural language generation. So we saw like natural language generation in terms of how things could be done or models could be created. So I mean, beyond this text input and output, we can also think about like the audio that is there. So we need to add one more layer of like, how do we actually transcribe this audio into text input? And at the same time, even in terms of like, how can we convert this text into speech so that it could be given as audio? And this is additional layer if you have personal assistants like a Google Assistant. So we talked a lot about this representation. So what are these representations? So this is how a system actually stores the knowledge inside it. So it could be in various form, and most of the systems, especially the commercial systems, are actually having a mix of all these. So it could be in terms of just the weights. So when we talked about those hidden states in an RNN or any kind of architecture, so that could be just in terms of what are the weights associated with it, or it could be in the form of like a knowledge graph. So that means a graph system explaining the different relationship between different entities that exists out there in the world. And that's why if you think about it, the human also knows. So one example I gave you was when John hit the car with the tree and the vehicle was damaged. So we have the knowledge about what vehicle actually means, like is it a car or a tree? So kind of representing that a car is a vehicle is kind of the knowledge representation in terms of knowledge graphs. And then we have rules around it. So there are definitely a rule-based system or expert system in terms of which we can try to store the knowledge. And then there are properties associated with it, which could be the attributes in a graph. If you think about a graph in terms of nodes and edges, so there could be attributes associated with both nodes and the relationship or the edges itself. So you can store those kind of representations. So it's going to be a mix of this, what we call them as like generally as representation. In deep learning world, representation is more like a pre-trained network that we can talk about, but generally it's going to be a mix of all these things together. And what is it used for? It is either used for querying. So that means we are querying this kind of like huge matrix of numbers in order to get if it is weights-based graph, or the specific knowledge in terms of like all the graph-based networks that we can think about from our like data structures. So trying to extract that kind of like querying and build a response to it. And then also trying to update. If there's whenever there's a chatbot and you give an input, your input is also processed again on top of it to build that delta factor that can add to this representation. So at a very high level, when you talk about natural language understanding, it's not just the understanding in terms of like there are several like components associated with the natural language understanding itself. So some of them are like sentence correction. So sentence correction is like, I mean, we can think about like the typos that could happen, the kind of like mistakes that people do in terms of using A and D instead of the symbol and, or people use like the apostrophe or even short forms. So how we can actually correct those sentences so that it has an easier way of trying to understand it. And then there is an intent classification. So identifying what is the intent of that specific chat that was sent, as in like the sentence that was sent by the human. So identifying the intent itself. Then identifying like relation. So you could say a long sentence and try and help the system to, sorry, not help the system, or the system tries to identify what are the different relations that could be extracted from there. And then there is a topic itself. So if you're talking about certain topic like a weather, and if you are getting some random reply from the chatbot, you would really not feel happy about it. So you want to stay on topic. So in order to do that, the system tries to identify what are the topics. And same in terms of sentiment and emotion. So you might have seen specifically with like these big company chat assistants that if you're saying something with a sentiment, it tries to reply you with a sentiment that goes with it. So if you're really happy about it, it gives you replies in a happy tone. And if you're angry about it, it tries to give you replies in terms of a calm tone. So having those kind of sentiment, emotion associated with it. And even in terms of speech act, like identifying whether it's an order or a statement, or if you're asking it to take an action. So all these things combined together actually forms this NLU unit from the previous slide that I showed you, the first part of it. And then there is an energy unit associated with it. So what it happens is from the representation itself, it has to extract the knowledge. So if you're giving an example of A, then it has to reply you knowing about what does that A mean, what does it mean in terms of context. Then if you're staying on specific topic, it has to identify all the related topics in which it can be able to provide you with more information. And then there is a response personality. So in real chatbots, there is a personality associated with it. And again, like this might not be 100% true, but most of the projects that we see in it needs to have a personality so that you can respond to a specific person with that personality, so that it now tries to understand you as if it's actually going to be a friend for you for some time. And then there is like what's the emotion, the associated emotion with it. And then there is like a main important thing is policy enforcer. You would almost never see a chatbot system to actually either use something like a swear word or be angry at you. So you have these kind of policy where you try to restrict what can actually come out of that. And even in terms of like sequence to sequence, if you're thinking about generating a response, it needs to have a sequence to sequence module, because now you're going to generate a set of text, and some of them could be the same thing that we saw before in terms of language model. How could we create those language models and use them as one of the sequence to sequence models? And almost always the answer that is generated, unless it's more not like a hobbyist chatbot, is that it generates a set of response and then identifies which which specific response would be the most ideal for it. So having that kind of module just to differentiate between which is the best response to send at the moment is also there. And then there is a template manager. As much as we want like the deep learning system to actually create a text on its own, like end to end, sometimes it's better to actually have a template manager where it tries to give you response in a certain way in terms of creating the template or the framework for the sentence itself. So these are some of those modules that are required there in the NLG system. Again, like there might be some additional modules depending on the utility or the use case for that specific system. But at this, so this is one of the things that these are some of the modules that I currently work on with the project that I'm working with one of the research groups at the university. So where are the conversational agents actually occur in real life? So it could be in terms of like the virtual assistants. It could be the booking tickets. So they are being automated more recently. The scheduling system itself. So now there are a lot of apps there, especially when you're working in a large corporate, that you just send a message and the system itself automatically books something for you. So the scheduling system. Then finding the right products for you. It tries to push you into certain directions, similar to how humans do in terms of like even the salespeople trying to push you in a certain set of products that you might find to be more useful. And then you have these kind of like return or exchange requests happening, a lot of online transactions, and then there is a customer service, and the more important thing is on the emotional support. So, all this while I've been making it generic. So one of my project with the university is called Automated Nanny Agent. So this is working in conjunction with Dr. Professor Osmar Zain from University of Alberta. So he is, he's the brain behind having this kind of chatbot, and this is kind of specifically providing emotional support for people, especially in the old age homes. And that is one of the projects that I'm really excited about, and hopefully we have a prototype soon for public to look at it. And then there is like in terms of education system, it tries to provide you more information, and that's something there. So chatbots, these are really interesting things, but they have grown leaps and bounds, but there are still a lot of things that we have to do in order to make it perfect. So one, I wanted to just like give you examples of like what are the different chatbots have failed, and some of them are actually dangerous too. So one example was the chatbot that was released by Microsoft. So it went haywire. So the one is called the Tay tweets, which you can see on the right end at the top. So it started learning everything just from Twitter and actually became kind of a neo-Nazist, a racist, and like a genocide friendly chatbot. So they actually had to shut it down. And same way in terms of like this OpenAI GPT-3. So it's a great model. It's going to be super helpful. It has some breakthrough research going into it. But can we replace it with, can we think about it replacing everything that a human can do? Probably it's still not in that state. So one example was that there was like researchers in France who actually tried to create mock patients and asked the GPT to actually talk to those mock patients in terms of what kind of like recommendation it gives. And in one of the cases, it actually asked a mock patient to go and kill itself. So it's still not there at that end where we could completely trust an end-to-end deep learning based system. But it has grown so much in the last few years that and it has been an incredible improvement in terms of research that is going on in there. Yeah, so with that, I'll conclude my talk. But before I actually conclude my talk, I also want to give a shout out to all the teachers out there, because I mean, I feel proud in coming and presenting here, but at the same time, I want to. I know there are a lot of students out there who might not say it enough, but on behalf of all the students that have been part of this your teaching environment, I wanted to just say thank you for everyone out there. Yeah, and I'll open the last few minutes for questions if you have any.
Okay, Talat, can you look into the comments? Like,
Yeah, ma'am. Yeah, I'm taking a look at the comments, and I think okay. Yeah, I have answered all the questions, I guess, based on what we have seen before.
okay, I'm allowing the participant to unmute, and if any questions are there, even participant can interact. I've unmuted, like all the participant has a permission to unmute yourself and ask the questions. Talat, what is the timing now there?
Oh, it's almost midnight for me.
Sorry, Talat. Like we,
No, no, no
we
problem.
disturbed your sleep actually.